Welcome to The Explainer. Today, we're diving straight into Chapter 11 of the acclaimed book, Designing Data-Intensive Applications. We are going to explore the core mechanics of how modern systems process massive, bounded datasets. Now, when we talk about processing petabytes of data, literally trillions of rows of information, it can sound like absolute magic, right? It's kind of intimidating. But the secret is that these massive, complex, distributed systems are actually just scaling up concepts you likely already know from using your own laptop. So let's dive into this and demystify how big data actually works under the hood.
To build our understanding, we're going to take a bit of a scale-up journey. Here is our roadmap. First, Unix tools to distributed systems. Second, storing data at scale. Third, orchestrating distributed jobs. Fourth, MapReduce and data flow engines. Fifth, the shuffle algorithm and joins. And finally, real-world batch use cases.
Let's kick things off with Section 1, Unix tools to distributed systems, scaling the single machine.
Imagine you're looking at a raw Nginx log line. This gets generated every single time someone requests a file from a web server. It's got an IP address, a timestamp, and the specific file requested, like a CSS document or maybe an HTML page. Now, if you only had to process a few thousand of these on a single machine to find your most popular pages, you wouldn't need some massive cloud infrastructure. You'd likely just use familiar, built-in Unix tools to make sense of it quickly and efficiently.
In fact, you could chain together a super elegant little pipeline using standard inputs and outputs. First, a tool like awk isolates just the URL from that long text string, which acts as our extraction key. Then, you pipe that output directly into sort, which takes those extracted URLs and orders them alphabetically. This forces identical URLs to sit right next to each other. Finally, unique-c scans down that sorted list and counts up the adjacent duplicates. It works beautifully. It seamlessly passes data right through memory buffers without breaking a sweat. It's simple, it's predictable, and it's incredibly powerful.
But what happens when your web traffic explodes? Once that dataset outgrows your single machine's local memory and disk space, we hit a wall. Suddenly, that elegant little Unix pipeline just isn't enough. To handle petabytes of data, we have to take those exact same operating system concepts, storage, scheduling, and execution, and map them onto a distributed cluster composed of thousands of individual machines, all working together as one cohesive unit.
Which brings us to Section 2, Storing Data at Scale, File Systems versus Object Stores.
The very first piece of our distributed operating system is the storage layer. Think of this as taking the place of your local hard drive. When architecting this, you generally have to choose between two main paradigms. On one side, we have distributed file systems, like HDFS. These are fantastic because they offer POSIX features and compute data locality. That means you actually run your processing code on the exact same physical machine that holds the data, which saves massive amounts of expensive network bandwidth. On the flip side, we have object stores like Amazon S3 or Google Cloud Storage. These decouple storage from compute entirely, allowing you to scale them completely independently of each other. But keep in mind, they treat objects as immutable. You can't just tweak a few lines of a file, you have to rewrite the whole thing.
Moving right along to Section 3, Orchestrating Distributed Jobs, the cluster kernel.
So, with our data safely stored across the network, we now need a job orchestrator. Think of this as the actual kernel of our distributed operating system, managing the pure chaos of thousands of machines trying to work at exactly the same time. Modern orchestrators like Kubernetes or Hadoop Yarn rely on three main components to maintain order. First, task executors run on each node, putting processes in isolated C groups to ensure they don't step on each other's toes or hog all the memory. Second, a resource manager keeps a global view of the cluster's health and the available hardware. And third, the scheduler. The scheduler actually has to solve an NP-hard problem, figuring out how to optimally assign thousands of tasks across limited CPUs in memory, all while balancing fairness and efficiency. Because a perfect mathematical solution takes way too long to compute, they use clever heuristics to make fast, good enough assignments to keep the cluster humming along.
But you know, a single batch job is rarely enough to actually solve a business problem. Usually, the output of one job needs to become the input to the next, creating what's known as a directed acyclic graph, or a DAG for short. To manage these complex dependencies, ensuring job B absolutely does not start until job A has completely finished and its data is perfectly ready, we use dedicated workflow managers, tools like Apache Airflow or Dagster. If you've ever built a data pipeline, you know this is literally the heartbeat of your daily work.
This brings us to Section 4, MapReduce and data flow engines, executing the work.
Now we reach the execution engine itself. This takes the place of our Unix pipes and actually processes the data we've stored and orchestrated. The legacy pioneer here is the map-reduce model. It forces developers into a very rigid cycle. Read data, run a map function to extract keys and values, implicitly sort the data, and then run a reduce function to aggregate it. While absolutely revolutionary when it was introduced back in 2004, MapReduce constantly writes intermediate data back to the distributed file system. Why? For fault tolerance. If a machine crashes halfway through a massive job, you don't lose everything. However, doing this heavy disk write after every single step can be incredibly slow and highly resource-intensive.
Enter modern data flow engines like Apache Spark and Apache Flink. These evolved to solve this exact bottleneck, and they were a massive leap forward. Instead of those strict map and reduce phases, they treat the whole process as a continuous flow. They pipeline data directly in memory between flexible, high-level operators, actively avoiding the local disk whenever possible. They only write out the final result to the storage layer, which makes them vastly faster than traditional MapReduce while still maintaining that all-important reliability.
And the crucial point here is that these modern engines also totally democratize data processing. Writing raw map and reduce code in Java used to be incredibly tedious and super prone to error. Today, these engines let you use familiar tools like relational SQL or pandas-like data frame APIs. You don't have to be a hardcore distributed systems expert to process petabytes of data anymore. Under the hood, their query optimizers simply translate your clean, simple code into highly optimized distributed execution plans.
Let's look a little deeper under the hood in Section 5, the shuffle algorithm and joins, moving the data.
What actually happens across the network when you run one of these high-level SQL aggregations or joins on huge datasets? How do different machines collaborate? This brings us to a brilliantly elegant solution, the shuffle. It's a foundational algorithm used by all these systems, and it manages the most expensive part of distributed computing, which is network traffic. When a map task finishes extracting keys, it partitions and sorts the data. The shuffle phase then routes all records sharing the exact same key, no matter which physical machine they started on, over the network directly to one specific reducer. Now, I know the term shuffle usually implies mixing things up, right? Like shuffling a deck of cards to create total chaos. But a distributed shuffle does the exact opposite. It groups and sorts the data identically across the cluster so the reducer can efficiently stream through it in perfect order without needing to hold massive amounts of data in memory all at once. And by leveraging that shuffle, we can execute incredibly powerful operations like a sort-merge join. Imagine you need to combine a massive stream of user activity events with a static user database. You can shuffle both datasets using the user ID as the key. The shuffle guarantees that an activity event for, say, user 104 and the database profile for user 104 travel across the network to land on the exact same machine right next to each other. The machine then just zips the two lists together flawlessly. It's a highly elegant solution to a massive logistical problem.
Finally, we arrive at Section 6, real-world batch use cases, putting it to work.
Let's see how this entire architectural stack builds towards the real-world applications that organizations rely on every single day. Because batch systems process bounded data reliably and predictably, they are literally the backbone of modern tech. They run extract, transform, load, or ETL, pipelines that safely integrate company data. They crunch the numbers behind business analytics in massive data warehouses. They iterate over vast datasets to train the machine learning models you interact with constantly. And they build derived data structures, like the massive search indexes that allow your daily web searches to return accurate results in just milliseconds.
But there is a catch. Everything we've discussed today assumes the input data has a known, finite size. The system knows exactly when it's done reading. This leaves us with a fascinating question to ponder. Batch processing is perfect for historical, known datasets for sure. But how do we architect a system when the data stream never ends? How do you sort something that has no beginning and no end? Well, that is the domain of stream processing, and it requires us to rethink time and state entirely. But we'll save that for another time.